Okay, everybody, welcome. What a nice showing this evening. And thank you so much for coming to our first Thursday Speaker Series webinar. Tonight, we're very fortunate to have a great scientist and researcher who hails from the American Museum of Natural History, and that's Russell Bicknell. So we have two Russells on with us tonight. So Russell Bicknell is the speaker. Russell Tarragon is our wonderful IT facilitator. So Russell is going to be talking about combining engineering methods with virtual paleontology to model extinct predators. And just want to get to a little bit about him. He completed his PhD and postdoc research at the University of New England in Australia. He has since moved to the American Museum of Natural History, where he is continuing his research. He explores aspects of arthropod evolution and morphofunctionality using a combination of methods within both 2D and 3D contexts. In particular, Russell uses 3D computational methods to understand the limits of arthropod predators and uses this area of research to highlight the interesting evolutionary history of the group. At this point, he's working on synthesizing various methods to more thoroughly model and understand extinct animals. We will make some announcements about upcoming events about Nesmia after the talk, and we will also have some time to have a Q&A. So without any further ado, I just want to mention how we met Russell. So last August, Nesmia had a field trip out to Plum Beach, and Mark Boughton, who's here on this Zoom. He was our naturalist and lecturer while we were out there, and Russell Bicknell attended, and that's how I met Russell. And so we had a wonderful field trip, and we did this in collaboration with Kingsborough Community College. And Christina Colon, who's also on this Zoom, she was the one who introduced us to Mark Button. So without any further ado, take it away, Russell.
Okay, thank you all for having me here today. I'm going to start by sharing my screen, and we're just gonna take it off. All right, so hopefully everyone can see that title page there. I've already had a very nice introduction, so I won't sort of reiterate this. But I think one of the take homes from what is probably going to be the next 35 to 40 minutes is arthropods, things with exoskeletons, are great. They're a brilliant model for understanding evolution, and they have such a rich fossil history that we can use them to understand a lot of different aspects about where life has come from and what has sort of formed the basis of modern biodiversity. So where are we in the tree of life? Well, this is us, right? This is a pretty decent representation of the modern biodiversity as well as fossil forms. And our arthropods, they form a really, really, really big branch of the tree of life. In fact, I dare say that if you were to think about a group of animals that really kind of summarizes true diversity today, and also in deep time, arthropods are kind of the ideal group. And we can think about this, in terms of like looking at percentage abundance. And like insects, they just really dominate in this particular figure here, right? So really, we're looking at a group that is a lot to look at. And I love this figure because this kind of summarizes that our marine arthropods just really are a decent hunk of biomass on Earth. In fact, the next big slice is fish, and then we have annelids, so worms and those sorts of things, and then we have arthropods again as the fourth slice, those are the on-land ones. And so Arthropods truly are, at least in my view, a system that is perfect for looking at questions of evolution. And we can then kind of step into looking at within arthropod groups, and we see the majority of these are basically flies, spiders, beetles, and wasps with much smaller divisions elsewhere. So maybe we want to think about looking at some of these larger groups if we're trying to understand aspects in terms of change through time. So that's your kind of crash course in like why arthropods are cool. But I think it's important that we talk about what an arthropod is. So arthropods, as I'm sure you all know, are animals that have exoskeletons, that have jointed legs. Arthropods have a very, very interesting evolutionary history. This is a very simplified phylogeny, what we call family tree of arthropods. And we're going to start down here as sort of what's considered the common ancestor for all of these larger groups. And these are things called radiodonts. These are beautiful fossil animals that we see from a time period here in Cambrian and also the Ordovician. They have these funky little oral cones that we think are used to kind of process prey, and they have these really nice, what we call raptorial or grabbing appendages, as we can also see here. And they come in a range of different shapes and sizes, and what's really been cool over the last kind of 10 years is we've seen this explosion of research into radiodonts, because they are kind of this what we call basal, this base morphology. I like that there's a cat here. It gives you an idea of scale of these animals. And we can also, like, because of this, has spawned a lot of interest in paleo arts. We have really nice, funky reconstructions of how these animals may have looked. So that's basically sort of an example of a possible common ancestor for all modern arthropods. The next group are our trilobites. Now, trilobites are basically the dinosaur equivalent of arthropods in the fossil record, and it's because they have a biomineralized exoskeleton. Here are some examples here with a bunch of different shapes, and we can also look at other examples of them. This is an example of a Cambrian trilobite that's rolled up into itself. This is very recent work that's been done by colleagues of mine looking at trilobites that have been preserved within ash, so basically Pompeii. And this kind of preservation gives us insight into exactly the minute details of these animals and how they may link to other arthropods within our family tree, our phylogeny. And of course, because trilobites have been so well studied, there is a beautiful history of sort of like artistic reconstruction of these animals. Next door to our trilobites, we have our chelicerates. So our chelicerates include animals like our lovely horseshoe crab, the entire reason why I'm here. We have sea spiders. We have an extinct group of animals called eurypterids or sea scorpions, as well as spiders, scorpions, and ticks. There are also other extinct forms like these little animals. Trilobites are kind of like, they're like spiders, but not quite truly spiders. And we have these animals. So this is an example of a sea scorpion, a eurypterid, that was about 2.5 meters long. So chelicerates kind of show one of the extents to which these animals can kind of push the size. And here's sort of an example of some of the other examples of large sea scorpions. So within sea scorpions, we have this very cool history of gigantism. And we're going to actually see that as kind of a theme as we look through the rest of the arthropods here, to give you that nice big framework. Next door to our chelicerates and our trilobites are the myriapods. These are our many-legged friends. And while these are pretty diverse today in the fossil record, they have some really, really cool examples. This is Arthropleura from this is the Carboniferous of Illinois, actually. Actually, this is Carboniferous of the UK. Arthropleura probably got up to about 2.5 meters long as well. So this was an on-land animal that really was kind of pushing the limit of size. And this is because of the Carboniferous. We have a lot of trees, we have a lot of oxygen, so these animals could begin to really push these limits. Then stepping more into this phylogeny, we see our crustaceans. Now, crustaceans are probably some of when we think of arthropods, maybe these are kind of the groups you default to. And crustaceans are brilliant. They're very, very diverse. I'm going to talk about them a bit later today because they're a really cool study system. And they have a really nice fossil record. And because they have these really cool shapes, it inspired some really sort of adorable reconstructions and artwork. But once again, crustaceans have pushed the limits of size. This is a coconut crab. Coconut crabs are big. This is a big animal. They have some of the largest pinch forces of crabs today. And then you got this thing, a king crab. So once these are modern animals, bear in mind. These are not in the fossil record. So today our crabs are really the animals, our arthropods, that are pushing that kind of that size limit. And then insects. So if you're not thinking about crabs, you're probably thinking about insects when I say arthropod. Of course, we've got our beautiful butterflies here with a range of different shapes and colors, bees and beetles and flies, our dragonflies. But then in the fossil record, we have this thing. This is Meganeura. Meganeura was about 2 feet long. Also from the Carboniferous. So at the same time, we had Arthropleura crawling on the ground. We had the largest dragonflies that we have ever seen flying around. So the Carboniferous would have been a really, really fun time to be a natural historian looking at arthropods. So that's kind of that's the summary. That's your taster of arthropods. They are, for all intents and purposes, a really, really good system for understanding questions in diversity, in disparity, in change through time, and in terms of understanding topics like predators and predator-prey dynamics. So this is kind of where the focus of my talk was really going to step in. A lot of my work that I do involves three-dimensional analyses. It involves bringing animals back to life, if you will. And then in bringing them back to life, we have the opportunity to analyze them with tools that are now becoming pretty commonplace within paleontology. Although when I started my PhD a while ago now, this particular application within arthropods was actually pretty fringe science. So we're going to look at some of the tools that I've used and what this has culminated in, and then what we can do thinking into the future. So I love these plots. Finite element models are just absolutely gorgeous. They're stunning. When we think about looking at predation in the fossil record, one of the key approaches that we can use today is looking at the actual predators themselves, and we can use a tool called finite element analysis, or FEA. FEA is an engineering tool that was basically designed to examine how building structures would deform under certain stresses, given certain input forces and material properties. So let's think of, I don't know, the Empire State Building, for example. And let's say we subject the Empire State Building to 8.0 earthquake. It's not going to happen, but in this example. And what we can do with those two pieces of information plus material properties, so brick and metal, we can understand how that building would deform, i.e. deconstruct itself, given those sorts of forces. Now, in the 2000s, it was kind of realized that this approach could be applied to animals as well, because basically animals have exactly the same situation. They have a structure, jaw. You have an input force, so the muscles that we use to close our jaw. And we have a reaction force, or nodes, so points that basically where we're going to be eating something. And this really spawned a new subfield within virtual paleontology, looking at three-dimensional biomechanics. And that's kind of where we're going to start today. So when we're looking at these plots, there are a couple of really key things to know. Areas that are blue are low stress, low strain. There's not a lot of force happening there. Areas that are pink and red are areas of high stress. There's a lot of force happening there. There's a lot of plastic deformation there and maybe failure. And the majority of work that had been done until I sort of stepped into my PhD was looking at vertebrates. So looking at sort of cats, dogs, canids, dinosaurs, and humans. But then I was like, why don't we try looking at arthropods? And since then, there's been a ton of really cool work that has been done, looking at scorpion pincers and looking at these animals down here that we're going to focus in on. So we're going to start by looking at methobasic spines. Anyone who's picked up horseshoe crab and looked at its legs, you'll probably recognize this. This is the leg of a horseshoe crab. And horseshoe crabs have these spines on them, what we call methobasic spines. They're basically the horseshoe crab equivalent of having teeth. And horseshoe crabs basically push their legs together to masticate prey with these kinds of spines. This is actually a pretty ancient kind of predation. And for the most part, horseshoe crabs are the only animals, well, almost the only animals today that still use this. There are a weird group of animals called copepods that kind of do something similar, but it's a different sort of system. Now, in the fossil record, we see other examples of this. So here we have the methobasic spines of an animal from the Burgess Shale, the Cambrian Age Burgess Shale of Canada, called Sydney and expectant. Sydney is one of those common ancestors, if you will. And here we have spines of Orlanoides serratus, a trilobite from the Burgess Shale, sort of elongate-looking spines here. And down here, we have an appendage of a trilobite from Australia called Redlicher rex. It has these little stout-looking spines. So we can look at these three systems, these three fossil forms and our modern system, and we can ask the question, do our fossil animals work the same as our modern system? Is this a good analog for understanding animals that we think are predators? And we can do so using finite element modeling. So when you're building an FEA model, you need to make a few assumptions. There are a couple of bits and bobs that go into this. Firstly, you need your modern system. Well, we're lucky we have our horseshoe crabs. Horseshoe crabs have a couple of muscles that they use to pull in these appendages. And so we look at our modern system, our horseshoe crab over here, and we say, okay, well, let's make the assumption that our fossil animals kind of work the same. And so over here with our fossil forms, we have used the same kinds of muscles that we have modeled here for our horseshoe crabs. So that's assumption number one. Then we need to reconstruct our animal. So with the horseshoe crabs, we can chuck in a micro CT scanner. It makes life quite easy. We don't need to work too hard to get that three-dimensional reconstruction. But our fossils are a different situation. Our fossils are a different system. They are preserved as two-dimensional impressions in rock. Now, no matter how hard you try, you will not get anything good out of a micro CT scan of a Burgess fossil. They are simply too pancaked. They're simply too cooked. So how do we then analyze that in 3D if we need a three-dimensional model? Well, we work with paleoartists to reconstruct our appendages in 3D, and this is what we have here. This is our reconstruction. And once we have these pieces of the puzzle, we can then run them through a series of analyses that culminate in some really gorgeous models, and frankly, some of the most amazing science I've had the privilege to work on. So, horseshoe crabs have three legs, three kinds of legs. They have a lot more than three legs, but they have three kinds of legs used in processing prey. You have your anterior walking legs here, you have your posterior walking legs here, and you have your pushing legs here. And if we remember what I said, looking at these models, we want to look at those areas that are blue versus those areas that are red. And for the most part, all these models have a pretty similar kind of off green-ish kind of color, with the anterior walking legs having a bit more of that red and the pushing leg having a bit less. If we look in now to look at these spines, that's where the processing happens. We see there's a lot of stress kind of taken up in those spines, more in the anterior walking legs than in the posterior. This makes sense. We know that the anterior walking legs of horseshoe crab are used to shred prey, whereas the pushing legs, are used to crunch shell. So horseshoe crabs are what we call durophagous or shell-crushing predators. So this is our model, okay? This is how we can use this to compare to our fossil forms. Sydney, that common ancestor I mentioned, the model basically looks exactly the same as a horseshoe crab. And so we can say, well, probably Sydney probably kind of worked like the posterior walking leg here. And this lines up with the fossil record because Sydney, there are some very rare specimens that have trilobite bits in the gut contents. So we know that Sydney was going around using these appendages to kind of grab and process and kind of crunch up prey. Redlicher, there's a lot of blue here, a lot more blue than there is in any of those hotter colors. And so immediately we're thinking, well, this thing probably didn't experience a lot of stress. And this makes sense. I mean, this is basically a nutcracker of an appendage. And we see this in the fossil record of the Emu Bay Shale as well. There's a lot of injured trilobites, there's a lot of injured Redlicher, and there's a lot of shelly coprolites or shelly fossil poop that are full of trilobite fragments. So what we think is happening here is Redlicher was, for all intents and purposes, cannibalizing other members of its species, and then using trilobites as a pretty healthy meal. But this leaves Orlanoides. So Orlanoides is kind of a bit different, a bit of a different story here. We see there's a lot of blue happening. So immediately maybe we're thinking, okay, maybe it's low stress. Maybe this animal is not experiencing a lot of stress. But if you look in the spines down here, all of that stress is taken up in that elongated spine. And what that means is this spine is very likely to experience some kind of plastic deformation, but likely also failure if it were used to try and tackle something that was pretty reinforced. So we think organoides is kind of functioning like the anterior walking leg of our horseshoe crab here, where its long spines are used to kind of shred prey as opposed to actually crunch down and process prey. So that gives you an idea of how we can use our finite element models to really bring animals from the Cambrian 500 million years ago back to life. There's another tool that we can use, another tool in our toolkit, kinematics. So biomechanics looks at how animals kind of functioned, kind of brings that aspect back to life. Kinematics looks at how animals kind of moved, how different parts of the whole are able to shift relative to each other. Think about my hand, how parts of my hand are able to move in conjunction with each other. Traditionally, kinematics has been the realm of two-dimensional considerations, primarily because 2D analyses are comparatively simple. They are not computationally complex, and thinking about something in a two-dimensional plane kind of removes a lot of the variation that's associated with that kind of thinking. But we live in a three-dimensional world, so we want to think about things in 3D. And that's where three-dimensional kinematics kind of steps in. And there's been a really nice shift in how often three-dimensional kinematics has been used within paleontology within the last sort of 5 to 10 years. There's been some very, very cool work that reconstructed dinosaurs to understand how dinosaurs moved. That's a really, really complicated question because there's a whole bunch of different parts that go into how those animals move relative to each other. And they have things like muscles that are kind of hard to reconstruct. So there's really cool work there. But our trilobites that I mentioned beforehand are also really ideal for this because trilobites preserve in 3D. And we know that they roll up. You remember I showed you that enrolled specimen before. So this is an example of a kinematic model of a Ordovician trilobite that was done by colleagues of mine. And this shows you how the animal kind of moved to protect itself. So using this new toolkit, maybe we can ask questions about like, well, how do predators move? And that's where these lovely animals come into play. So whip scorpions and whip spiders, the animal on the left here, have these really incredible anteriorly directed, what we call raptorial or grabbing appendages. And these animals are really, really good at eating other things to the point that there's records of like whip scorpions eating frogs. So these are very effective on land terrestrial predators. But we also see in the fossil record these similar kinds of appendages. This is Anomalocaris. It's an Ordovician, so about 480 million year old sea scorpion that has similarly these very large anteriorly directed appendages forming what we would call a capture basket. So we can ask the question, well, do our modern animals move the same way that we think our fossil animals do? And if they do move similarly, well, maybe we're seeing some kind of convergence on a similar kind of means operation. And that's a really interesting thing that we can ask. We can begin to build models to tackle this exact same question. So when we're building these kinds of models, we similarly need to either scan our animal or we need to reconstruct our animal. And once we've got our scan, we can kind of split up all little pieces or little bits and bobs of our arthropod. We're lucky arthropods have a segmented body plan, a segmented parts. So basically we can just kind of chop off each different section. And then we can set them up to kind of rotate or move relative to each other. And when you do that, what you see is some really, really cool results. Our sea scorpion, our whip scorpions and whip spiders, our modern arachnids over here, form a very, very similar capture basket to our fossil animals, or at least how we think our fossil animals work. And so even though the appendages aren't the same, so the arms, if you will, are not the same in between these two groups of animals, the structure that is formed is the same. Our modern arachnids, we know, are using these appendages to capture vertebrates as well as invertebrates, whereas our fossil forms, we're probably going after sort of fishes and other sort of marine, probably relatively slow-moving animals that were then able to capture and then bring closer to their mouths for processing using this secondary pair of appendages. So this combination of looking at the past and the present gives us a means to once again bring these animals back to them. But let's take one more step here. Let's ask what happens if you combine these two methods. Now, usually in the space of virtual paleontology, we don't go this road. Commonly, we will stick to one kind of methodology because there's a lot of information that we can glean from these approaches anyway, and it does become computationally untractable to keep adding on more bits and bobs. And it becomes, a project can very easily kind of spiral beyond the original focus to really kind of pushing the limits of things that, you have to build a really large team. But I decided to do this. I really wanted to do this. I wanted to understand this animal. This is Anomalocaris canadensis. This is like the first apex predator, maybe. And what I wanted to see was if we reconstruct this animal as it has been proposed, which is that it was swimming around in the ocean and it was picking up trilobites and it was eating trilobites, could it actually do this? And by combining kinematics and biomechanics, we actually were able to do this, which is really, really cool. So we need to reconstruct our animal first and foremost because we're looking at the Burgess Shale once again. This system is not designed, well, system's probably the wrong word, but this deposit is not ideal for scanning material. It is too compacted. The carbonized fossils do not have enough density difference between the rock themselves and the fossil for them to get any kind of information out of a scan. But Anomalocaris is probably one of, if not the most charismatic Cambrian animal, if you can call something that looks like a cuttlefish charismatic. And because of that, there's thousands of specimens have been documented. And so we were able to use a whole lot of data to build this three-dimensional reconstruction, which is the most accurate two-scale model of the appendage of this animal. And once you do that, once you have your model, we can then ask the question, how did it move? And, well, we have our modern system, we have our whip scorpion and our whip spiders, and we know that they use their raptorial appendages to grab and then move prey closer to the mouth for processing. And when we look at our fossil system in Anomalocaris over here, very similar. In fact, pretty much the same thing. The only difference is Anomalocaris has more segments. It has what we call more podomeres. So this raptorial predation, absolutely, this animal was doing that. That's brilliant. We can confirm that. Anomalocaris canadensis, one of the first predators, was using its anteriorly directed raptorial appendages to grab prey, but was it able to grab trilobites? Was it able to grab animals that had biomineralized exoskeleton, effectively a literal suit of armor? Well, that's where our biomechanics, our finite element analyses come into the question. And when you build a biomechanical model of Anomalocaris using sort of the two end members of our kinematic analysis, so outstretched and enrolled, what you see is there's a lot of those really hot colors, a lot of pink, a lot of pinks, a lot of reds. That tells us no, this animal actually was not that well designed for taking down biomineralized prey items. And especially when you look at like these long, slender spines, what we call endites, really there's all of that stress is being taken up in those spines. So chances are this animal actually would have experienced failure, would have broken itself if it tried to grab hold of something that had a biomineralized exoskeleton. And we know this kind of from the fossil record because there's one example of an injured Anomalocaris appendage out of thousands. So that really tells us that this animal was not really keen on a crunchy diet. It probably had a more soft-bodied diet. And that kind of is reflective in what we see in the Burgess Shale. A lot of the animals there are soft-bodied. A lot of them are swimming around in the ocean, probably in similar environments to our Anomalocaris. So this is a really cool combination of those two questions. Now I'm going to take one more step to where I'm currently working. I'm working in crabs. I love crabs. Crabs are a brilliant system for understanding predation. And you may be looking at it going, why? Well, there's a couple of really, really important reasons. Firstly, crabs are really diverse. It's a lot of modern crabs. A lot of different animals mean that we have the opportunity to look at a bunch of different shapes and sizes, which is cool for comparative contexts. Secondly, crabs preserve somewhat commonly in 3D in the fossil record. All the other examples I spoke to you about require us to build our animal from two-dimensional impressions into the 3D. But if we have a fossil that we can scan, we don't need to do that. We can actually use the animal itself in our analyses, which gives us the opportunity to start asking really good questions about whether or not the way we're reconstructing them actually makes sense. So it gives us a really cool study system for testing aspects of predation as well, and testing how we're understanding them. And thirdly, a crab pincer is really simple. Like, it is super easy to build one of these things. And in fact, pincers have been evolved at least 5 times completely independently across arthropods. So as a structure, really, really good at dealing with a bunch of different kinds of life aspects. And it's so simple. You basically have a fixed section here, a propotus. You have a movable section here. You have your dactyl. And then you have a big muscle mass. That's it. And all this does is it tightens, the muscle tightens, and then the finger closes. And that is how it works in predation. Now, I mentioned that crabs have a really large amount of shapes and sizes. And this is just a small smattering of the scans and the reconstructions I've done. I've done at this point, I think, 85 species of crab, including some fossil animals. And I've begun to analyze them. And what you're going to see as I kind of click through here is that even though the shapes and the sizes look very, very different, they're all experiencing kind of a similar stress distribution. So the majority of that stress is kind of taken up along that movable finger. And that makes sense, right? Because this is where we're expecting the majority of the force basically to be sort of focused in on. And this is where, of course, crabs are using their appendages to bite down and grab hold of prey. So that really gives you an idea of, and this is really ongoing work, but what this is beginning to show us is even in a very, very diverse group of animals, like crabs, we're still seeing a consistent application of a structure used in predation. And crabs, it seems, are kind of optimized. Their claws are kind of optimized for this exact thing of closing and then grabbing hold of prey. Okay, so that's kind of the research side of things. That's the fun stuff that I do. I love what I get to do. But let's think about this from an educational perspective. So I showed you all a bunch of really cool models, and I showed you some really cool stories. But there's kind of a more pertinent question here of how do we translate that into an educational context? Now, I can sit in front of you or stand, as I am, in front of you all and give you a lecture about why virtual paleontology and virtual biology is really interesting. But in a classroom context, that's not particularly helpful, especially if you're trying to reach students. In the modern age, it's more and more common that our students are in some way attached to the internet. And so we can use three-dimensional data within a teaching context. It's becoming more and more common. Examples here, you can get you can access a surface scan of a mummy coffin, and you can look at all aspects of that surface scan. This is really interesting within teaching. It gives students a tangible way to actually relate to content that maybe they don't necessarily have access to. Three-dimensional reconstructions are bridging a lot of gaps within accessibility, within inclusion as well. And they are allowing students that may not have the opportunity to go to museums to virtually attend museums. I mean, there are limitations there. It's not the same as breathing in dust, but it does allow your students to engage with material and see ideas that they may not actually have been able to think about before. And this is becoming quite a common thing. Like, we're seeing more and more that as scientists such as myself are making mass data sets to address complex questions within evolution, that we're making this data available. And once data is publicly available, it is then within a framework that can be accessed. And in that context, as teachers, you now have the opportunity to really engage with that material, to actually utilize the stuff that I'm producing for your own teaching ability. And this is really looking like it's going to be kind of one of the next main directions within teaching. As we bring the third dimension into the classroom, we're already three-dimensional beings, but in a digital context, we're developing a space in which students can begin to engage with this kind of data and they're going to ask really cool questions about, well, how can I get to work with this kind of stuff? In fact, I think some of the most fun that I've had with students is within 3D data. I think students really love the opportunity to like spin a model round in a three-dimensional space and kind of mess with it and engage with it and then ask questions from that. And it's just a really good resource called Morphosource that I'm going to step us into, and hopefully this will work in Zoom. We're going to touch wood and hope this functions correctly. And hopefully this will open up a new tab. Oh, we're almost there. Yay, fantastic. Morphosource. This is brilliant. I love Morphosource. Morphosource is great. And it's all free. So morphosource.org is a open access platform where people are depositing micro CT scans, CT scans, MRI scans, but they're also depositing the three-dimensional reconstructions of these things. So while I don't expect you all to be intimately familiar with how to deal with a micro CT scan, which is a whole process, what you do have the opportunity to do is look at surface scans that have been uploaded as like really, really high resolution models. I really like this one over here, looking at colors of skull anatomy. I'm going to open up, I'm just going to just click through some of these just to give you all an idea of what you can use. You can use this data within your teaching. So yeah, here we go. We have what looks to be some kind of snake skull with all of the different bones segmented or split up into the different parts, and that have then been color coded. And there, actually, if you look from sort of like the top down, that's pink and that's pink. That's actually, those are the same bones that are basically just mirror images of each other. And over here, this looks like a turtle. I'm going to say it's a turtle. That looks like a turtle to me. And so similarly, once again, we have like the same plates have been color coded to be the same, even if they're mirror images of each other. And then we have like all different parts of the animal. And you can then download, you make a login to do this, but you can download them and you can open this kind of data in like I think like 3D Viewer, which is a default Microsoft software, will allow you to open this kind of data. And for those of you who use Mac, I'm sure there's some kind of Mac equivalent. Now, when we think about Morphosource, it is kind of like hard to navigate sometimes. You need to kind of know what you're searching. And so if you are thinking about kind of getting into this, I would say give yourself like a half a day to kind of search a bunch of different things. Because there's a bunch of different kinds of data here, so both from archaeological as well as zoological as well as paleontological data, and the data formats do vary depending on what people are kind of interested in doing. And so you, as an end user, kind of there is a little bit of a learning curve there, but this is all information that you can access for free. It's all a really nice way of engaging with your students and saying, well, yeah, I mean, we all like digital data, like I like video games. Most kids like video games. And this is basically just a logical application of video games within a teaching context. Okay, so I'm gonna stop talking now. I think that's been about 40 minutes of you all hearing me blab. So I might now just acknowledge the community for giving me the opportunity to talk here, as well as the AMNH who've supported me, and I might stop sharing my screen and I open up for questions. So thank you all.
Oh, thank you so much, Russell. That was fascinating. I learned so much, and also just the resources that you're showing as well. I think everybody, all teachers can use and take advantage of. But let's try and see what reactions we're getting from the audience here today. So now is our opportunity to ask Russell any burning questions that you have on your mind. So I guess I'll lead off with with my question. So I was really interested in your opening slides because I wanted to know what the stressors were that produced that large size. And in the Museum of Natural History, especially with there's one exhibit there of the bottom of the ocean somewhere near the Antarctic, I think, um, which shows very, very large crustaceans and fish, and really ginormous. And so I was just wondering what could have been some of the pressures. I don't want to put you on the spot, but just to give the audience an idea of what could have possibly produced that large size in those times.
So there, there, there's kind of a cheeky, easy answer to some of them. Ooh, I want to. There we go. Animals on land, when they're exposed to large amount of oxygen over multiple generations, will get bigger. In fact, one of the limiting factors in terms of body size today is oxygen. So the Carboniferous, where we saw those really large millipedes, centipedes, and that dragonfly, this was the point in time in which we had really, really big trees. And so lots of oxygen meant that these animals could get really, really big. In terms of the marine conditions, that's kind of a different system. Our really big sea scorpions, some of them basically hit that space of being an apex predator. And once you get to be so big, like you kind of fall into this weird body size realm where you're too big to be eaten by other things, but you're so big that you need to keep eating other things. Kind of hit this kind of like cap there. But they also do a bunch of other weird things. So also during the Carboniferous, we see our sea scorpions, but they're living in kind of freshwater environments, like in streams. And they look pretty big at this point too. And I think that's probably to do with the fact that there wasn't a lot of things that were targeting them. So modern day horseshoe crabs, for example, for the most part, are pretty opportunistic eaters. They'll have whatever they can put in their mouths. But we look at the fossil record of horseshoe crabs. They've been pretty small, whereas horseshoe crabs stay pretty big. And so what we think's happened is that horseshoe crabs kind of hit this like evolutionary like stasis. They stopped changing, but they kept getting bigger because there's nothing really targeting them. And I think so within those other Eurypterids, those sea siblings, that may be kind of what's happening. And then trilobites are their own group of animals, which are basically, they got so big because they had a literal suit of armor protecting them. And when you are covered in, basically calcite, there is not many things that will try and eat you.
Okay. Very, very interesting. Um, uh, Audience, would you like to ask questions? I don't want to monopolize the whole questioning platform here.
Thank you so much. I really enjoyed it, the presentation. So this program, this Morphosource, does it allow you to manipulate and change the images that are on there?
As in when you download them,
Yeah,
can you mess? Yeah. So you as an end user can't mess with the data on
right.
the platform, on the web page, but once you've downloaded it, then it's free for you to do whatever you'd like.
Right.
Yeah.
No, it looks really cool. Again, like you said, a lot of high school students were really game players and so on
Yeah.
would be into it. So you just showed the images that you concentrated was just on the head. Do they have ones of the whole body?
Yep.
Or is that
Yep. There's like full-on scans of like entire animals.
fantastic? Thank you. I really enjoyed it, and I think it's applicable in the classroom.
Thank you very
Thank you.
much.
Yeah, I really enjoyed how you mentioned bringing animals back to life to analyze their predation mechanisms, and I never really thought about it. I just looked at the horseshoe crab on the beach. I knew that the movement of the legs would crush up whatever they were trying to eat, and I never went beyond that thought. But I think Mark Button has. So let's hear it from Mark. Go ahead.
Hi, Russell. We got to go for pizza one of these days.
We do. Yeah. We gotta
But
go for
on a
pizza.
serious note, looking at like the stress points on the claws of different arthropods, do you have a way of assessing muscle strength, or just looking at the stress points on the exoskeleton?
Yes, you can kind of do that. So when you're building these models, I don't go into too much detail because it becomes just messy to talk about these kinds of models. But you have basically an input force. So you have a force that you can derive from your scan, which is basically what we call cross-sectional muscle area. If you want to think about muscles as like a tube, and you like a pen, and you took like the longest cross-sectional area, and you calculated that area, that is basically a proxy for muscle force, or muscle force input force. Now, what you can do after you've run your model is you can then go to the points that you can constrain, those points that we know that's where the prey item is going to be, or at least we're modeling where it will be, and you can calculate what's called the reaction force. This is basically if you think about pinching yourself, like what you calculate there is the amount of force that's translated from the input muscle force through the process of closing the appendage into the output force. And so there are a bunch of different steps that we can kind of get more information on. I don't often do that for fossil animals, because if you're reconstructing an animal in 3D from a two-dimensional fossil, you're already in the space of the compounded assumptions to the point that you don't want to go too far. But I am doing it for the crabs. I'm really interested in doing this for crabs because we can take the what's called the mean von Mises stress. So it's basically a number that represents that entire model, and we can take the mean reaction forces, and we can combine those two pieces of information to build like an adaptive landscape, to look at where crab claws have kind of peaked in terms of their functionality. And that gives us a really unique way of assessing these kinds of finite element models that, for the most part, there's a ton of data that goes into them, but oftentimes we don't focus on that. We focus on the depiction of those models in terms of that sort of that heat map. But we can do a lot more, and that's kind of where that's where my research is more geared these days. That's a good question. Thank you.
I was thinking about how to use this on the beach in a field trip, and maybe we wouldn't have the connectivity to be able to see the diagrams, but I mean, we could print them out, for example, and then look at the legs of the horseshoe crab molts, and to be able to start a conversation on the beach about predation mechanisms in the horseshoe crab at least, but maybe if we found some other types of crabs, we could continue that conversation over into more crabs. Well, other
Yeah.
crabs, into crabs. Sorry.
Yeah, absolutely. I think like we do. So I do teaching over the summer here at the museum, and we take students out to different beaches, and we look at basically the biodiversity in these beaches, and we can talk about predation in that context. Basically, any kind of structure that probably has its use within tackling another kind of animal is or falls into the realm of something that can be used within that framework. I mean, my beyond the crab stuff that I'm doing, I'm starting to look at like spider fangs, because spiders are very, very diverse group of animals. I've looked at scorpions. I want to look more at scorpions and these weird groups of animals called camel spiders, sulfugids. They have really, really big pincer-like things. And so there's a whole bunch of questions that we can start to ask, and we are starting to ask as we begin to like look at how we think about predation.
Very interesting. Yeah, so while you were talking, I was also thinking about or the variety of crabs and how there's so many different size variations depending on I guess the location where they're living and the resources that they have and what they're eating and preying on. And it seems like it could be a great conversation, either, as Lou said, in the classroom or out on the beach in a field trip. But I imagine that you could be using this conversation for all of the marine animal groups that you could possibly find. As we saw in your opening slides, they were terrific. And I love how you juxtapose the fossils inside of your tree of life diagrams. I'd like to be able to get a copy of the one that looked like a huge map. It was
Sure.
really beautiful, beautiful. Is
Lisa, you have two
anybody?
people with their hands up.
Yes, go ahead, Jason.
I really love the presentation. I kind of based off of what you were talking about with the crabs, I was really interested in, do you see I guess the measurements of stress like changing across different, I know you said the different claw shapes didn't really show a lot of big changes. Do you see them changing across different like trophic levels, like decomposing crabs versus active predator crabs? Is that something that you've seen a lot of data on?
So that's kind of the next step for this project, is basically then kind of diving into like what do each of these taxa, what do each of these genera do in terms of their position within the ecosystem. And so that's actually a forthcoming question that I'm planning on answering. What I'm also really especially interested in doing is looking at sort of the bilateral asymmetry that crabs have. If you think of like fiddler crabs, right? Male fiddler crabs have that massive claw, and they've got the little dinky one there, right? And so structurally, I'm interested to know, even though these very, very, very different morphologies, are they exerting the same amount of force or like scaled to size? Or is there actually something that's mechanically different between these animals? And I think, yeah, that's really kind of the next step there. I mean, there's a bunch of different, I only showed you like 30 models. I've made, I mean, if you looking at like both claws, we're looking at somewhere close to 180 models that I ran, which, to give you all context, that's an insane number. Like, that's just like, no one does that kind of data gathering. I'm just nuts. I just love crabs. But it gives us the opportunity then to really delve into understanding more about the structure and looking at both sides of the animal. So an answer, I don't have an answer, but it's where we're going.
Thank you for
I
that.
think
And
Christina
has her hand up.
Hello.
Hello.
Hey.
So my question, Russ, is yes, one, when are we going for pizza? And two, what about those male claws on the horseshoe crabs that are the biggest of all the claws, and they're not for predation at all, but they're for holding on to the ladies. And so one, do we see that kind of appendage for latching onto other, latching onto the other sex in other invertebrates? And two, is there any research being done on the morphometrics or the relative size of the claws on a male versus his overall size in terms of his potential mating success? I don't know.
Yeah, I mean, in terms of like the modified sort of boxing glove like thing, yeah, you're right. As you said, like they're used in basically to puncture and then hold on to the female during mating. So yeah, they have absolutely no application within sort of predation at all. In terms of like looking at that structurally, yes, actually, there is a paper that came out a couple of years ago that looked at a bunch of different like modified appendages I actually looked at that trilobite that I mentioned, Orlanoides serratus from the Burgess Shale, and then a bunch of other arthropods that have sort of similarly modified appendages. It's rare, but it is there. It's also within the fossil record. We have two examples of horseshoe crab fossils that have that modified appendage, which is really, really cool. Within like looking at linking the success of male individuals to the size, or I suppose robustness might be a better term there, of that modified appendage. I don't think that's been done. I don't. It'd be a really cool study system, especially as we see across the four modern horseshoe crabs that morphology actually varies depending on the genus and then on the species. And so there's probably a really cool question to be asked, maybe thinking about like the size of that, like investment in that morphology versus the rest of the body size, thinking about like male peacocks, for example, because if that morphology is really, really important in the attachment and not sort of being washed off, which we know that it probably is, then theoretically we could expect to see maybe some more those individuals that have that kind of investment are more fit in that context. But I don't think anyone is doing that. That's a really cool question. Thank you.
Thank you.
Well, Russell, your presentation tonight was fantastic, and we thank you very much for your time and your talk. I also want to thank Russell Russell Tarragon for his IT facilitation of this event this evening, and Lou Siegel for the production of the flyer and promotion throughout our platforms to make sure that everybody sees your presentation. And of course, our members will be able to access this recording from our website. And so if anybody here is not yet a member, go right to the webpage, become a member, and then you could see 2 years worth of recordings. So there's a plug-in for that. I want to make sure I say that, Sarah. And also want to remind everybody that coming up March 20th, we have a Zoom program with Sea Grant members, and they're going to talk about their program. So we're looking forward to that. And then also we're arranging a field trip with Sea Grant to an oyster hatchery place somewhere out on Long Island. We're looking forward to Lou's Priscilla boat trips once again. Can't wait for the weather to warm, and then I'll be out there. But what I really enjoy is the after parties and the dinners that we have at local restaurants after these wonderful field trips. I hope you're coming back from Florida soon, Christina.
I'm already back.
Oh.
You don't
Okay.
say that very gleefully.
Well, let me just put it this way, that they've got nice crabs in Florida and they're year round.
Yeah.
So
Yeah, of course we miss that year-round weather, right? So
Lisa, you also should mention the conference, May 3rd.
yeah, so well, why don't you talk about it, Sarah?
Well, hi, everybody. On May 3rd, the NISMIA group is having this annual conference at SUNY Maritime in the Bronx. We have a fantastic speaker, Carl Safina. We have a panel of people who are going to talk about marine careers and engaging students, and many fabulous workshops and field trips. And live registration will be available pretty soon, in a day or two. So check out the website. And if you're not a member, definitely join NISMIA, because you have to be a member to attend the conference. And there's going to be 3 fantastic meals throughout the day on May 3rd. So we hope to see you there.
And also, it's our 50th anniversary that we're celebrating. And so the New York State Governor has sent us a citation acknowledging that, and that will be read at the conference. And then Sarah's going to have a wonderful, wonderful historic archival game for us to play.
And there's going to be a guitar player who plays throughout the day, and there's going to be a big cake in celebration of our 50th anniversary. So it really is a full day of fun and eating. like Lisa
So we
said,
look
it was
forward
a
to
plus.
seeing. Yep. So we look forward to seeing everybody, and if anyone needs a ride, let us know. So thank you so much, Russell, again. Thank you. Thank you. We really appreciate this. It was great. We look forward to working with you more in the future. I think there's great potential for us to be able to create material for our teachers and educators who are members of this association. Thank you, everybody, for coming. It was a real treat to see you all, always is. And we look forward to seeing you soon.
Bye. Thank you.
Thank you so much. Bye.
Bye-bye.
Thank you.